Okay, exponential function. A lot of similarities to everything you've learned this year with functions. It's just a little different equation and graph. Okay, so we're going to learn what an exponential function is, and then we're going to graph them. And there are some science applications here we'll talk about today and tomorrow. Might help you in biochemistry, more in bio than anything. First of all, let's compare and contrast. Let's see. I should start. In the beginning was the word. You've all taken AP Bio, right? Or you're in it?
Yeah.
We talked about bacterial growth.
Yeah.
I mean, what model does that follow? Yeah, it follows an exponential model, right? So you will have a time zero, correct? Yeah. When your bacterial seed, if you're getting a sinus infection, it will seed in your sinuses with like 2 bacteria, right? And as time progresses, it will grow exponentially, right? Until, can it grow exponentially on forever? Sure, I hope not, because that means you're dead. But at what point you're dead, does it still keep growing? Oh, at some point it runs out of food or something, right? So realistically, bacterial when we model population growth or bacterial growth, it's never going to sustain this model. Okay? Never. We will run out of a resource at some point, right? In this case, your sinus infection, your body will start fighting the bacteria and eventually kill it off usually. So most of the time you're going to see this taper off back down to 0. If it doesn't, then you're going to die and the food source is going to run out. Okay, so mathematically we can say these, mathematically we can say that it goes to infinity in behavior, right? But realistically, that's probably not going to happen. Time will still go on to infinity, but the y value will not ever continue up indefinitely. Okay. So it's a good model for shorter time periods. But we have to be realistic about what we're looking at there with exponential functions. Okay. These functions come in a form of something like this. So this would be about as straight as it gets. It's the same family of function format that you've seen. Okay. This would be our growth rate. Here's our start value. If I were to, I'll graph this right now. What does that number do right there? Thinking families of functions. What is adding?
So that's the shift.
Vertical or horizontal shift?
Horizontal.
Why is it vertical?
Sure.
Why is it? Do you agree with her? Because she threatened you?
No.
It's the vertical
That's
shift.
never stopped me. She said, do you agree with it? Because she wants to fight you. I was like, no.
Dude, if it's horizontal, it would be growing like
If it was a horizontal shift,
this way. Nothing grows like that. It's not exponential.
it would be in that. Remember, the horizontal shift always with the x value. So if I had like -2 right here, that would shift it 2 to the right. This shifts it 1 up. So, I'll graph a couple of these for you, but same families of functions, knowledge that you've been looking at. Where do you notice the x's that we've never had an x value? No, exponent. Yeah. Right, that's why it's an exponential. Don't confuse it with this function. They're two different. They're two different functions. This function in the negatives, y equals x squared will look like that, right? Whereas an exponential will actually just continue on that direction. What did I do with that? Okay. So there's just a couple differences that you want to pay attention to. This is a power function because the x is in the base, and then here's the exponential. So try to keep those separate in your knowledge. Good? Alright, so you know what an exponential looks like in the basic format. Let's graph I'm going to do several here. Or the x. You can do these on a calculator. You know how to do an exponential on a calculator.
Put the caret.
Yeah, it's 4 caret x. So that's a possibility. I'm going to try that. It doesn't matter. The only time degrees and radians matters is in trig function. Okay, so you can graph these by hand, and the best way to do it is a table of values. What's 4 to the 0? 1. Who said 0?
Me.
No soup for you. What's 4 to the 0? 1. 4 to the first? 4 for the second? Okay, so 0. Why are you drawing that like that?
Why are you drawing your table like side
I like it that way. I like it. I never draw a table.
1, 4, and then 2, 16, right? So what about over here though? What if x is negative 1? Yeah, it's 4 to the negative 1, right? Which is 1/4. If x is negative 2, 1/16. So you see what's happening as we progress to negative infinity? Closer to what?
0.
0. It's just going to keep getting closer. We'll never hit 0.
No.
So this is called a asymptote, right? Oh, great. I heard that. that's y equals 4 to the x.
Can you go back to 1 second?
Yeah, that. What? Oh, I thought you said first grade. I was like, wow, thanks for that. Go visit my daughter. Okay, so general exponential there. Let's throw in a few other changes. What does that do to it?
Oh, yay. So that shifts it down to.
Down 2, right? So everything's down 2 units. What's my asymptote? Y equals -2 this time, right? Okay, so again, using families of functions knowledge, right? About
That shifts it to the left 1.
yep. So everything's going this direction 1 unit, right? Whoops, that's not very accurate. And what's the asymptote here?
Isn't it supposed to cause that? Oh, wait,
It's still y equals 0. It's just shifted left. There's no up or down shift. Okay? Yeah, 1 to the left.
So it's not like one of those things that's like real confusing where it says -2 and you're supposed to like go up instead of down. Remember when we first left, and they were all like that?
It's the same concept. If it's connected to the x here, then you're an opposite way. Here, this means move left 1. Right. Okay. The y values are, remember, up and down, these match. I only have one more up here. Number in front, what is that going to do?
It's going to make it negative or positive. That's not true. Yeah.
Yeah, it's going to be steeper,
It's gonna change the
right? What else is it going to do? This is where exponentials change just a little bit. Is it going to change these number, the y-intercept? X is 0, y is now 2. Okay, so this changes the y-intercept. Even though it's not a plus something,
So
it does change the y-intercept. And it's steeper, so every one of these will be multiplied by 2.
So it's 8 into.
But it still follows the asymptote at y equals 0.
That's a lot of lines on that graph.
Yeah, it is. You're right. Go ahead, add another one.
Yeah.
I need to.
Yeah, let's go the opposite direction.
What would be the inverse of this?
The inverse of.
We will get to that. Logarithms.
Oh, dang.
Bother interrupting us. Have fun. Hello. Yeah, he's on his way. You bet. Oh, okay, look at this one. It means move it left 1.
But how do you enter it?
Oh, Your calculator should put it, it's still that caret. And then you should put x plus 1 up here. Okay, what does the negative do in front here?
Should you say it's down?
Reflects it.
Oh, the other across that line.
Yeah, across the x-axis. Yeah. So this green one is the exact reflection of the purple one. So, not accurate, but you get the idea, right?
Yeah.
Okay, and then if I put the negative in the x, what is that going to do?
Then it should reverse the y-axis.
It reflects it around the y-axis.
What?
Here,
Your
write
x
it
is
down.
negative.
Okay, one more here.
What was the asymptote?
It's still like 0. Okay, the orange, the negative is in the exponent. That's a reflection over the
Y-axis.
y-axis. Okay, so that's going to be so lots of different things. Again, you've learned most of those. Just reapplying them to exponentials now. The only difference you really see is this number and what it does to the y-intercept. Okay, so this is exponential growth. Because this number here is greater than 1. The base is greater than 1. Good? It's called exponential growth. What would the number be for exponential decay? The numbers between 0 and 1. So exponential decay for between 0 and 1. Yeah, I know it's boring. I swear that's bad too. Anybody else? That's what exponential decay looks like. So when you get into the negative exponents, right? So we'll throw it off. What is 1/2 to the negative 2 power?
Negative 1/4.
Remember from 2 days ago?
Oh,
What is
it's
it?
2. It's 2.
It's 2 over 1 squared, which is 4. Okay, so what you end up doing actually with the negatives is making it grow in this direction.
You lost me. How does it just become 2?
The negative exponent, remember?
Yeah,
Means
like you-
reciprocate.
Oh, okay.
So we flip the fraction. Now 2 squared is 4. What's negative 1 going to be?
2.
2, 1, 1/2, 1/4. Okay, so you can see that it reflects it around that y-axis. Same rules apply for everything else that we just looked at on the last slide. Okay. Can anybody think of any applications in science for this?
Bacteria.
You're telling me that bacteria, as time goes on, tends towards 0.
If you're trying to kill it.
Like human beings.
Yeah.
So here,
So trying to find it.
bacterial death.
Yeah.
Okay.
What about a human being?
I can hear you. Brain cells. So you're telling me as time goes on, you have fewer and fewer brain cells? Maybe in Colorado. About what? Oh, criminals.
No.
Let me I just.
Oh, tremors.
Telomeres, that's what.
Telomeres, that's
Yeah,
right,
telomeres.
that's what it is. As you age. Yeah, so, as you age, your telomeres get shorter. Right? So, yeah, your telomeres, that might follow this model, I don't know, but that's a good thought. The best application for this, is carbon dating. Or Half-Life. Not the video game. Right, so carbon-14 dating. I think carbon-14 decays, half of it will decay in like 5,600 years. Right, so every 5,600 years, half of it will decay, and then it comes out to eventually, will it ever all be gone? No, it's half and half and half, will never be 0. It's Wednesday. Thursday.
Your homework is posted on Classroom.
Not Wednesday, it's Thursday.
You want to write it down? Yes.
Mickey Carpenter, Rail Win.
Yes, it's Wednesday.
Garrett Hunter,
Yeah.
Wednesday.
There you go.
Oh, dang you.
Have a nice rest of the day.
You moved it.
There we go.
Two?